First of all, show of hands, how many people have heard of shifter rail? Not as many as I'd like to hear, but that means then I presume even fewer have maybe heard of In2Track3. Yep, thought as much. Okay, I'm just going to go through an overview of really what this project was about and what's going on at the moment. So, shifter rail has been going for around about 6-7 years. It comes to its conclusion at the end of this year. In2Track3, which is one I'll talk about in a minute, and more on projects we've been running through Network Rail's involvement, that finishes in December. But shifter rail's been going along for a while, and it's actually a European-funded project. And the reason why Network Rail are involved, with 25 other partners that are actually all spread throughout Europe, is that European funding is available. So effectively, we put in 56% of the budget. The European Union matched that with 44%. So clearly quite a nice carrot dangling there to actually make sure you can get some innovation move forward at a cost that's actually shared across everyone. The other advantage of having shifter rail as a project with In2Track3 in this case is that you can actually look at work that's been done by all the other partners that maybe Network Rail isn't involved in, and we can still sort of call on that information to try and actually look at where we want to take some innovations out of that project and look at what we can use that information for. So sort of there's a raft of projects going on. So Network Rail's projects, we have, I think, around about 25 going on at the moment in this project. So shifter rail's looking at innovation programs, or has been for the last 7 years. And obviously, as you can see there's various different IPs, innovation programs. We're really talking about IP3. So obviously track infrastructure, looking at how we can actually look at making it more cost effective, more reliable, with what we've got in track now. But also the other part of that is looking at next generation. What is the next generation S&C going to look like? So the joint undertaking with part of the European Union asked us to look at a horizon of 40 years in advance. Quite a difficult thing to do because clearly we don't know what sort of technology is going to be developed during that time. So clearly we're trying to actually stretch where we are now in terms of technology knowledge and move forward where we can possibly do with something that's tangible with technology as it currently stands. But clearly there is a question mark about, well, what technology is going to change in that 40-year period as to what we can do next. So shifter rail's had all these projects. So starting back in, I think it's 2016, 17, Interrail, that was just another sort of satellite project to actually look at setting the scene from a point of view of what do we want to do? How does it actually work forward? Then it started with In2Track. That's talking about just track work in terms of looking at issues we have currently with our current network, current type of S&C and plain line, and what sort of defects we have and problems that we need to try and actually find a way of designing out if we can do, finding a solution to actually help us maintain it better, get it more efficient so with what we have now. And also looking at what the next generation is in terms of S&C and track. But what happened with the In2Track projects is we're talking about a very low TRL level at In2Track itself. And as we go through the projects to In2Track2, In2Track3, it's just increasing the TRL levels of those particular work streams to actually look at what actual stage we can get to in In2Track3. Well, we've got to sort of TRL 5 and 6, so we're talking about prototypes, first of type, proving technology. All these other projects, which I won't go into too much because it'll take too long to actually explain, is basically all little stepping stones to actually move forward from one project to another, all funded by the European Union. So clearly there's an awful lot of work going on through these projects, which unfortunately it sounds like not many people know about what's going on there. But clearly we need to actually make sure we actually shout from the rafters what's been going on, because some fantastic pieces of work has been progressed through these projects. So I'm just going to talk about In2Track3 at the minute. So ultimately it's got split up into work packages. So there's work packages we're involved with, the 5 there. And I'm just going to talk about work packages 1 and 2. So 1 is obviously looking at S&C we have currently in track and what we can do to enhance that, make it better, make it reliable, improve componentry and that type of thing. And next generation is work package 2, which is obviously looking at that 40-year horizon I mentioned earlier. We've also got 2 which we're involved with heavily in the plain line side of things. So they mirror the S&C one. So you've got one for about track as it currently stands now. What can we do to improve things we know of defects, etc., that we have that really aren't just unique to Network Rail, but across Europe. and what's the next generation track going to look like. So clearly, from Georgia's presentation about what HS2 are looking forward, that's obviously looking at innovation and trying to actually change what we do and make it more reliable and obviously cost effective in terms of its long whole life cost, which is where this is sort of hedging to actually go forward with. So a few things that we've just been developing through this project over the actual In2Track2, In2Track3 situation are things like this. So ultimately, work I'm involved with, University of Birmingham, have basically been looking at trying to put sensors on a crossing. You think, well, that's not novel. Well, it is in a way, because we haven't got a portable system that, from a TME's perspective, you can't just go and put something on necessarily easily on the crossing itself. There's other conic systems, there's other yellow tech and other things that are around that do similar things. But this is really looking at the acceleration of a wheel set going over the crossing wing rail to nose. Obviously, we've got an issue with wear and tear, having height difference between the nose and the wing rail. You get more acceleration as the gap gets bigger. So if we have some parameters in our standards that says, if you get a height difference between the wing rail and nose of X millimetres, whatever that is, if you go above that parameter, the chances are you'll get a crack crossing. That's the sort of information we don't have for our TMEs at the minute, out there trying to manage their crossings, and we don't manage crossings as well as we should do. So having something like this that could actually give that parameter and information to a TME, he should hopefully be able to act on that. Obviously, we can give them all the information they want, but if they don't act on it, it's not going to be actually going to be any benefit. But obviously, we have to give them the tools for that job. So that's what University of Birmingham are looking at. So we're going to a site in Bawtry to actually look at that on the East Coast Main Line with Soren to actually help us with actually putting one of these on track to see what information we can actually see from a real life situation. Then there's a handheld scanner here, which is something which, when we look back in derailment terms of what we've done in had accidents in the past, so Princess Street Gardens, for people who may remember that far back, 2012, 2011, and Shrewsbury, they were the last really big 053 derailments we had. And at that time, with the RAID recommendations, we were actually challenged to actually try and actually look at introducing alternative technology that didn't actually mean we're relying on human factors to actually make a decision that's quite critical and quite safety critical in this sense. So looking at how we can actually adapt and make a tool similar to that. So that is obviously a computer generated image, but actually physically exists in that shape. And it sits on the actual switch rail and stock rail, takes a scan, just one shot with a laser, and then actually looks at superimposing the actual P8 profile, which is our most common wheel profile on our network, which is what we have on our track gauges. And the three lines there you can vaguely see have the different angles of contact that might actually mean we've got a derailment issue or not. So it's taking the human factor issue out of that. So that's at the stage where we've got now a prototype ready to actually go out and showcase and show people what it actually does. So anybody at Rail Live that went on the APTA stand, that was there, along with another one that they're developing. Another one we're looking at the moment, which was at Tuxford's RIDC site yesterday, is the RFID tag. So ultimately, you think, well, okay, it's identifying where we are with the crossing nose and the switch toes in this case, of what we're trying to actually put RFID tags on the track. The reader that you can see in the middle picture there is on the train. The train's going to go over that, it'll pick up where that actual RFID tag is, which is basically saying this is where the toes are of the switch, this is where the crossing is. So we can then more accurately align where our track recording traces actually show where the S&C is. So clearly you can see a bit more visibility about where we've got geometry issues. The reason why this is sort of quite key for us is as Network Rail sort of evolved from British Rail to Rail Track, etc., computer systems started being generated to actually allow us to look at where S&C was situated. So people might remember Joggis. That's obviously now obsolete. It's all been sort of morphed into what we have in our S&C Ellipse database. But unfortunately, all these legacy systems are saying the switch and crossings are here, maybe 4 or 5 meters further down the line for another system. Another one's saying it's 10 meters that way. There is a lot of confusion as to where the actual S&C is. So try and actually have some real-time information that can actually show that is what we're trying to achieve in that sense. And we're going to be testing this next month to actually show that the technology works. Another one which involves cladding of switch rails potentially was a sort of a difficult question to say whether we actually think this is going to work or not. But effectively what we're going to do is clad some rail which has been, we've got some test pieces that have been done by the University of Sheffield. They've actually clad some rail We're going to test it on their test rigs to see if it actually has some more wear resistance. So effectively, if we can find that this actually works in terms of the adhesion of the cladding system to the rail, potentially we could then adapt that to something on the switch rail. So we can try and find a way of seeing if we've got more wear resistance on the switch rail, where we can actually add the cladding to make sure we try and sort of make the actual asset last longer. So that's a bit that's actually going on at the moment with the University of Sheffield and a cladding company. And one that Jan, who's talking about various things from the University of Huddersfield later on, has been working on optimising the NR56V crossing profile. So people in the track engineering fraternity might have heard of NR60 Mark II, as that's the latest S&C type that we have, which makes a lot of sense in terms of the work that went into the geometry of that. So they optimised the actual crossing profile of that type of S&C at the time of the design. But NR56V is sort of the old £113. It's never really been updated that well to make sure we can actually bring it up to state in terms of the requirements of our infrastructure, trains, wheel sets, etc. So Huddersfield have done an awful lot of work on modelling the multi-body simulation of what the actual profile should be to reduce the impact load and the acceleration as the wheels traverse that area. So there's two crossings that are on order at the moment with Progress Rail. They're going to be delivered thereabouts in the middle of September, that we can install at a junction somewhere near Nottingham, and we can assess how the actual profile actually marries up. And clearly, if we get the right data back and get the information we're hoping to, we can change the profile of our crossing going forward to actually make the asset last longer and make sure it actually performs much better than what we do with the current situation. And another one, 3D printing of components. You're thinking, well, 3D printing is blooming expensive, which it is. But when you look at the amount of different S&C types we have, the 90 different components that means we've got, there is some sort of scale of cost there. That means if you have something come off of an S&C unit, you need to replace something as a particular bespoke component, it could take 12 months maybe up to trying to find the actual mould, if it still exists, if it's an old one, and also the cost of getting that actually manufactured. Clearly, the timescale between a component breaking and being needed and the casting process being able to actually manufacture that might be a long time lead time. So clearly that might mean we have lots of schedule late payments because we've got a speed on a S&C unit. We can 3D print something in a week or less. So at the moment we've got two components, which are these two, a stress transfer block and a housing that have been 3D printed, and we're going to put them on the testing, which basically is in the fasting system for the EN fasting system tests that we would normally expect all our components to go through. So once we've got those done, then we'll put them on test. The shapes that you see on the right-hand side of each of the components are the shape that we're going to have, not the actual original one. Effectively, the company who's been working on this has optimized the actual shapes, so they can say, we can save this material. We actually obviously can reduce the amount of material needed, we can reduce costs, but it still maintains the integrity and the performance we expect from that component. So again, we're stretching the boundaries about what we can do with areas where 3D printing might be something we can use. And obviously, the additive manufacturing side of things mean we can play around with the material type to give us different requirements in terms of what performance we need on certain aspects of that component, where we get the wear, etc. We can change what that component surface is compared to the main material. So it gives us lots of possibilities to try and expand on that technology. And how many people have heard of Repoint? A small number. Repoint is, for those who don't know, is a concept that the University of Loughborough basically brought together about actually changing a type of switch rail we have to move trains from one track to another. Instead of having conventional switches, stock rail switchblade, you have this system. Now, I don't know if this video will work. We shall see. Oh, there you go. So it just moves the whole rail, full head section to full head section. So effectively, that's what the concept is. It's nothing new, because if you look back in the 1800s, it was something that was sort of mooted about then, but clearly the technology wasn't around to make it happen. So we've been working with the University of Birmingham, who've taken this on from Loughborough to actually develop it as far as we possibly can, more on modelling than anything else at the minute. But we are creating one of the bearers that they've got there, the three bearers at the top. They're the drive bearers that lift everything up. The ones at the back are just there for more support than anything else. And that will actually give that motion to move it in an elliptical movement side to side. So we obviously, are looking to try and actually see as far as we possibly can do, because clearly developing something like this is very costly, to prove the concept. And that's the type of joint that they're looking at, to actually not have just one flat piece of rail butted up against a flat piece of rail, because clearly it's a joint, which isn't going to be good. So they're looking at something that's obviously similar to a sort of expansion switch type arrangement for that. So that's, again, what we're trying to move forward in In2Track3. And there's a bit more about the bearer itself for moving the actual rails up and down and across the actual change in position. And obviously the advantage of this is we're taking the switch rail out of the equation. So where we've got O53 derailment hazards, we've got problems obviously where we need competent people to actually do the actual checks. We need equipment to look at that. We have the derailment risk because of the actual lateral forces on the switch rail. With this, it's more going to be like a train wheel going around a curve than actually having the switch rail. So it gets rid of an awful lot of the issues we currently have. Yes, it introduces some additional risk with that joint, etc. But again, it's looking at what we can actually see from the next generation type of S&C in future. And Mark Wakeley is going to be talking about drone work later on. So basically, a part of the project, we're now going flying a drone over what is Wigston North Junction, which you can see on the right-hand side. It's on the left-hand side as well with the drone. Looking at drone inspection of S&C. And you might think, well, okay, what's special about that? You could just put a video camera on it and have it going flying over while you're looking at the screen and seeing what's actually in front of you. This isn't anything like that, apart from the fact it's the same sort of drone that could fly over there. So this takes still photographs. The software knits them together, gives you an orthographic 2D view and a point cloud view. So we can then zoom into that particular footage quite closely. You can take dimensions from it. You can look at issues when we're looking at pattern recognition, which again, Mark will talk a little bit further about later on. So we're also looking at developing pattern recognition for componentry, clips, etc., which we've proven does work, because if you put two inspection patterns together from the same S&C unit over maybe 3 months, I think, in terms of what we had, you can see clips and things like that moving in terms of the footage difference. So it's quite an intelligent thing to try and actually emulate, using drone footage, something similar to PLPR, which is where we're actually heading. So again, moving forward with what we're actually trying to achieve with our inspection processes and keeping people off track. And this will still be able to see something you can actually use while trains are running. So it's not a case where we're going to interrupt services to do inspections as we currently do most of the time. And that's the type of footage you can see. The bottom one is the one I was saying we've highlighted obviously on the componentry, looking at what actually is seen. And if that cursor, I can't move it on this one because it's obviously just a still photo, but if you move the cursor backwards and forwards, one of those clips either moves or it's missing in the next footage. So either side of that photo are two different, so from that green line, you have one inspection on the left-hand side, one inspection on the right-hand side. Same footage, different dates. So that's an easy, quick and easy way for people to see what's actually happened over time in terms of changes. And you can take dimensions as I showed you at the top there in that photo. And one or two areas on the graphs there, looking at cant and gauge. That was an early version of that we did in In2Track3. But you can see there is some areas where we can actually use that footage to actually look at cant and gauge by measuring and putting different values in there to show. I think the red is the track gauge itself, the manual track gauge, and the green is what the actual drone footage was able to show. So there is quite a good correlation that needs some work on it, but obviously it's close. And having a portal to actually show a section manager or an inspector how they can look at what the actual inspection's done. This is another thing that Mark's actually helping develop with his team, and how we can look at this as an inspection tool in the future. Lastly, anybody heard of discrete defect repair machine, DDR? One or two of you. So this is a big program where we actually have been looking at an S&C version of the DDR. So the DDR is a discrete defect repair machine for repairing defects in plane rail autonomously by actually putting it over the defect, basically setting it up and pressing go, and it actually mills out the actual defect, deposited weld material to actually build that cavity up, and then it mills it back to profile that's either side of the actual defect. We're also pushing the boundaries to actually get one that's actually able to do the same for a crossing. And this is where this is showing the actual details of how they can mill out a crossing using a plain piece of rail in this instance, so we're not wasting crossings. But effectively moving forward from the BV1000 situation where you can actually automate repairing a crossing by actually having the wing rail and the crossing nose repaired at the same time, and then making sure the angle and the profile from the geometry requirements and the height difference in terms of what you want to make sure it's a stable situation in terms of the acceleration the wheel sets will put on the actual system are actually maintained regardless of the actual wear either side. So the DDR and this actually measure the profile of the rail using lasers before and after where the actual extent of the repair will be taken, and it will merge that in when it's blending in the actual milling of the repair to get it to a state where it sort of blends into the either side of the actual repair rails. It doesn't have a big lump or anything like that after the repair's carried out. So quite a lot of work going on in that sense. We're going to some trial of that, I think, in September. And that's me. I'll hand over to Jaydan to do.
Thank you very much, Phil. Okay. So, we'll start from here. So this is the data that shows about 5 weeks on or 1 week on from the installation that happened at Reading West. So as you can see from that data, we had some Connex monitors on, and it looks really good. It's essentially as flat as a pool table, so it's exactly what you'd want to see a week after doing an installation. Unfortunately, about 4 weeks after that, I get this email or this photo come across my desk in an email. Now, the alignment on that, or the longitudinal alignment, does not look as good as you would want it to. So what we have to do now is we have to go and find out exactly why it looks like this and whether or not this is a genuine problem or it's not. So out on the inspection, we had some manufacturers. We had Voestalpine come out with us. And as you can see, that little green mark there is a fleck mark that they put on in the manufacturer's yard. And it is very slightly not lined up there. It's 2 or 3 millimeters not lined up. And that was the case for quite a lot of the bearers, but quite a few of them were still aligned. And then you can see on that blue photo, we've put a new fleck mark on. So when we go and do a new inspection, we can see whether or not it's still aligned. Now, this slight misalignment may have contributed to the total misalignment we've seen. Now, we can also see this is the sort of direction that they've actually moved in. So the joints and the bearers have moved in a direction opposite to travel. And unfortunately, we can't tell whether or not both roads have moved or whether or not a single road has moved. And the reason for that being is we don't know the exact position of where it was on installation. But what we do know is how much they have moved between the two inspections, the first one and the second inspection. So as you can see, on the first inspection, the worst ones that you get are up at 30 millimeters offset longitudinally. On our second inspection, we used a slightly more accurate tool and none of those offsets had increased. So from my perspective, it's very unlikely there's been any additional movement between those inspections. Looking in a little bit more detail, we've got 3 photos. One was the day it was installed, one was the second inspection, and one was the third inspection. So looking at it the day it was installed, those first 2 photos over on the right-hand side of the screen, they look very ever so slightly misaligned. So what that means is that there were some bearers that were not aligned perfectly, and as you can see, those are the ones that have moved the most after 1 or 5 weeks after the installation. And that movement has gone from a very small to roughly 30 for the first and 26 for the second, and then 22 for the first and 17 for the second inspection. However, there were some bearers that were completely perfectly aligned on installation, and those ones have moved from up to 5 millimeters at the first inspection, and 19 at the second, and 19 at the first and second inspection. So what that means is that there are some that have moved where there was no movement on the installation day. Now, some other things that we've looked at. So if you take the toe to nose, nose to nose, and toe squareness, you can see that while all of the measurements on site at the inspections were in tolerance, they were not perfect. So the toe to nose is +11 and +5 respectively, and nose to nose is -9 millimeters. Toe squareness is -4 and -5 millimeters on both. So what that essentially means is that in comparison to the manufacturer's yard, these set of switches are slightly out of alignment. And I think that has contributed fairly significantly to where the longitudinal movement has ended up. In addition to that, if you separate out the bearers roughly where the panels are jointed, you can see on inspection 1 and inspection 2 that some of the panels have significantly more movement than others. So it increases towards the middle where the crossing noses are and then decreases further out to where the toes would be. And if you look at the misalignments, you can say that the likelihood of those misalignments is actually coming from when you lift the panels in and you put them down, it's very difficult to line them up perfectly. While it is still well within tolerance, it looks as if the joint has taken this difference from in the manufacturer's yard and just shifted ever so slightly. The key thing here, though, is that even though looks like there is a longitudinal misalignment, there are no defects related to this. There's no faults and no defects. There are no gauge issues. In addition to that, I also got another email reporting that there was a dip angle on one of the crossing noses. So what we looked at the traces, and it doesn't look as if there's an issue on the trace. And when we went out to site, there was no issue with the running band on either of the crossing noses. And watching a train go over it, it's completely solid, it's completely flat. So the dip angle that was reported was much more likely to be the design dip angle that you get in the freewheel area of a crossing. So in addition to that, 5 weeks on, taking a look at the Connex monitors, it is still completely flat. So taking the Connex monitors that were installed, the four Connex monitors, 2 on the A and 1 on each of the A and B end of the crossing noses on both sides, there's no movement. So taking that with the inspection that we did, I'm happy to say, or I was very happy to say, that the misalignment is not an actual problem. It is just a visual feature that is a little bit unpleasant. There are no defects and there are no failures associated with it. And the likelihood of one forming from any further misalignment is incredibly low. So the maximum misalignment we had was 30 millimeters. And for us to go down from 1435 to 1434, it would have to be a maximum of 43 millimeter misalignment. So I don't foresee any problems there. And that is the end of my presentation. Thank you.